presentation here in this very nice place in Natal, in this International Institute of Physics. So this is the title of the talk. We'll be talking about the some theoretical proposal of rotating sonic black hole from spin-orbit coupled BC, and this work was done with my PhD student Inderpit Kaur, and the funding is from the Department of Atomic Energy from a generous fellowship for by that which allowed me to come here and travel up to this distance and present this work. So this is Inderpit and this is another student. I have a very small group of ultracold theory in IIT Delhi, and this is a picture of our institute, Indian Institute of Technology Delhi, which is one of the 5 old IITs in India. And this will be the layout of the talk. First we'll very briefly, after an introduction, we'll introduce the model system. Then we'll point out the theoretical mechanism, hydrodynamic formalism, under which one can show that such system can generalize analog rotating sonic black hole, and how to map the corresponding metric to something called btjet metric. Btjet is proposed a 2 plus 1 dimensional model of the rotating black hole, and then we'll be talking about the details of the profile of the potential in which the condensate evolution was simulated, and the structure of the density evolutions and various other things. To give you a little bit of background of this particular problem, I would just like to start with the following slide. So deep connection between effective field theories of condensed matter and quantum field theory, and these being particularly in workshop on quantum simulation. So there is a lot of scope for very interesting quantum simulations, and throughout the deliberations you have seen various interesting things like lattice gauge theory and other things. So the analog with the sonic black hole comes from the fact that the wave equation that describes the phononic propagations in a fluid can be interpreted under appropriate condition propagations in an effective relativistic curved space-time background. So this was an idea first proposed by Andrew and later on expanded by various people. And this allows one to study, since making a direct experimental observation on a real black hole is very difficult, things like event horizon, Hawking radiation, and etc. can be understood in an analog tabletop experiments. And for example, an event horizon for the sound wave can be described as a boundary surface through which the corresponding fluid flows, and that boundary surface separates the supersonic and the subsonic design. And there has been very interesting theoretical proposal, first in the context of ultracold atomic condensate in 2000 from I think Innsbruck group, and then it was first realized experimentally in Technion by Jeff Steinhauer group in 2010, and then there was a subsequent very interesting experience of observing analog Hawking radiation by the same group which was reported in 2014 and also in 2016. So this was basically a snapshot of the experiment which took place to show that sonic black hole in this system. So the condensate was moved left to this particular waterfall potential, which translates the condensate towards the left. And when the condensate falls through this particular waterfall potential, it gets accelerated. So at some point of time, the condensate velocity exceeds the velocity of the sound, and that gives the division between the supersonic and the subsonic rhythm, and the horizon is created by such very sharp potential step. And there has been very interesting simulation afterwards to observe Hawking radiations and stuffs like that. And very recently, there is also another very interesting simulation by Ian Spellman's groups in NIST, where they have actually simulated a rapidly expanding Bose-Einstein condensate in the form of an expanding universe, and obtained and have seen things like redshift for the phonons and other very interesting cosmological phenomena. So that gives us some motivation, and the basic theoretical framework is like this, that essentially the BEC which you consider, that is considered as a phonon vacuum, and if you consider the ground state of the BEC is something like a phonon vacuum, and when you consider in the hydrodynamic limit the fluctuations over the density and the phase operator and write down their effective equations in hydrodynamic terms, then this effective equation essentially takes the form of a Klein-Gordon field in a curved space-time background, and the corresponding metric that actually, and the corresponding metric that has the following form in terms of the sound velocity, which so c square here stands for the sound velocity, and v corresponds to the various components of the condensate velocity. So you can write down this metric is in the following form, and from there you can actually find out the location of the corresponding event horizon. So this type of equation actually from this idea, so this was the idea proposed by Andrew in 1981 that you can actually define something called an acoustic metric, which is very similar to 1 plus 1 dimensional generalization of Schwarzschild metrics, which was used to describe a static black hole configuration. So as compared to that, here c is the velocity, cs is the speed of the sound, v is the fluid velocity, whereas in the case of the original case, this vf is essentially the free fall velocity, and c is the speed of the light, and the Schwarzschild times and the radial coordinate here is just replaced by the one-dimensional coordinate and the typical time, real time of the flow of the corresponding condensate. So very soon after Einstein proposed his general theory of relativity, so this idea of the Kerr black hole came, which actually pointed out the rotating black hole, and almost all the real black holes, they are essentially rotating, so they have very important degrees of freedom of the angular momentum. And rotating black hole has somewhat different configuration as compared to the Schwarzschild black hole solution, and so the event horizon is apart from the event horizon, one of the very important thing in the rotating black hole is that there is a region near the event horizon which actually drags the space-time along with that, and that also rotates. And this particular region between the outer and the inner event horizon is what is known as the ergo region, and that demarcates a rotating black hole from a typical non-rotating Schwarzschild type of black hole. So in the case of the Schwarzschild black hole, essentially the ergo region and the event horizon, they coincide. So a rotating black hole is actually generated at some particular stage of the stellar evolution from a spinning star. And you can, all of us know about these recent LIGO experiments of the detection of the gravitational waves, which has actually generated due to the collision of two such rotating black holes. So we considered a typical spin orbit coupled BEC. So I will not go much details into this particular model. So eta and eta prime are essentially spin orbit coupled parameters, and so this model was described in quite detail in this particular reference which I pointed out. And one can write down the effective second quantized Hamiltonian and then do this all standard tricks like writing the atom photon coupling and then do the rotating wave approximations and projection to the dark state manifold. And after doing all these things, when this system is projected to the lowest subspace, because it is going to form a Bose-Einstein condensate, the system can be, system's dynamics can be defined by this corresponding Gross-Petrovsky equation. So here psi kappa corresponds to plus and minus are the two components. So this is essentially a two-component condensate, and this particular time-dependent Gross-Petrovsky equation will be simulated through a two-dimensional potential profile, which I'll be showing in the next slides. So what is the main issue? Why we get interested in the spin orbit coupled BEC to look for the rotating black hole? Because in the rotating black hole, of course, so the question is that what is going to be the vacuum for the corresponding phonons, which is going to obey some hydrodynamic equation whose metric will be given by some similar metric like a rotating black hole. So one of the very easy suspect is the spin orbit coupled condensate, because spin orbit coupled condensate has this very interesting property, since the corresponding Gauss-Petrovsky equation looks like a gauged version of the Gauss-Petrovsky equations with an effective non-abelian gauge potential. So this usual form of this curl of the condensate velocity equal to 0, which actually happens for a scalar condensate. So no vorticity exists in a scalar condensate unless you rotate this particular system. In the case of the spin orbit coupled condensate, they are actually, even without any external rotation, because of the presence of this gauge field, some type of diffuse vorticity actually existed. So there is a very interesting paper by Stringer in 2007, and also how the system behaves under the rotation that was in detail analyzed in some papers, including Professor Fetter was here, so in one of his paper in 2014. So this is the particular property of this spin orbit coupled condensate, which tells us that this condensate has some type of distributed rotation even without any external applied rotating field. So this system's hydrodynamic equation might be the a possible candidate for such rotating black hole. So we consider, since it's a 2D system, so instead of the typical waterfall potential, 1D waterfall potential which was considered in the experiment, we have considered some 2D generalization of such waterfall potential. In this case, the condensate is initially prepared at the center of this potential, and then you gradually closes this particular top of these potentials in an adiabatic way, so that the system, the condensate finally faces the sharp potential barrier from all directions, and it falls through it, which is going to create the corresponding event horizon. So then you do a very bit lengthy but reasonably straightforward hydrodynamic approximations in the limit that where the polarization component, which is essentially the difference between the density of the two components, is much smaller as compared to the typical total density. So you write the corresponding density and phase variables and do the necessary algebra, and at the end of the day, you will end up with this particular form of the Klein-Gordon equation of the Kerr space-time for the phase which is conjugate to the total density. And this is where, so this is where I have written that this is where the rotating sonic black hole lies, and we'll just show very quickly at what it is. So if you now look at the corresponding metric of this particular equation, then one of the very important difference as compared to what happens in the case of the scalar condensate, that in a spin-orbit coupled condensate, the expansion is anisotropic, and as a result, if you look at the various velocity component, they are also in this particular case, they are going to be anisotropic, and that has very interesting consequence as far as the rotational features of this black hole is concerned. So one can now write the corresponding line element of the distance, and if we write and convert it into the plane polar coordinate, then one can actually show that it directly maps with the corresponding metric for the so-called btjet black hole. So the btjet was the name of the three authors who first proposed this 2+ 1-dimensional model of this black hole, and that is the form of this one. So this is of course a canonical analog, but if you look at this term, then one get this particularly extra piece dt d phi, which has a finite line element in front of that, and that is somewhat proportional to the angular momentum. So that actually shows that how this particular system is going to map into the btjet black hole, and one gets the condition for the ergo region by equating the coefficient in front of dt square equal to 0, which actually gives the region where the only Vr square equal to Cs root over by 1 plus alpha. Alpha is essentially this anisotropy factor that actually give you the event horizon. So one can see that as long as the condensate is going to have a finite angular component in this velocity, then even though it will be very small, but it will be theoretically possible to distinguish between the event horizon and the corresponding ergo region. So this system is a very fit candidate to generalize such this one. So here I show the corresponding numerical simulation based on the time-dependent Gauss-Pitavetsky equation. This center region white, so this is a time evolution for the two values of this anisotropy parameter. One is for a relatively lower value, another is for a relatively higher value. So you can immediately see that as it, so this region, white region inside, that is also a subsonic zone, and the outside this entire circle, that region is also a subsonic zone. As the system propagates, a very interesting feature happens, which is associated with the formation of what is known as the black hole regime, that because of the nonlinearity, the system actually successively get reflected back from that nonlinear potential, and that actually leads to some type of self-amplified oscillation of this corresponding BEC, which is sometimes associated with the self-amplified Hawking radiations in this particular system. And also for a higher value of this anisotropy parameter, one can also see, apart from forming these rings along the radial direction, it also forms some very interesting interference structure along the azimuthal direction. So that shows that this particular system has also substantial azimuthal flow, even though that is much less dominant as compared to the corresponding radial flow. So another feature of the rotating black hole. This is also the typical structure of the line of this element of this corresponding metric. We have particularly plotted this one, which actually very nicely corresponds to the corresponding density plot. And then finally, I would just like to show, so this is how one can separate out between the event horizon and the ergo region. So the event horizon is just associated with the radial component of the velocity, where is the, so this type of conditions which is going to be the event horizon and which is going to be the ergo region, that essentially comes on setting the conditions on the corresponding metric component of the metric in front of the various line elements, and that gives you a very clear definition of the difference between the event horizon and the ergo region. Now, as I pointed out, that typically in such condensate flow, the angular velocity is much smaller than the radial velocity. So generally, at a lower value of the anisotropy, it is very difficult to identify between the ergo region and the event horizon. But as one goes to the higher and higher anisotropy, one can see started small separation develops there. So we have essentially amplified one portion of this. So this is a plot of the velocity, and one can also see somewhat unlike the real black hole situation. So in a real black hole situation, one is going to be a purely a superluminar regime separated with the subluminar regime with an event horizon. In this case, the transition from the subsonic to the supersonic is not completely continuous, but it forms some stratified region of this existence of these ring patterns. So there are regions where it is almost continuous, and there are regions where, because of these oscillations of this coherent matter wave, there is a repeated structure of this supersonic and the subsonic type. So this feature was also observed in the 1+1 dimensional black hole simulation, which actually shows that this black hole has very interesting structure. Like, it has not only has one single horizon, but it has an inner horizon and the outer horizon, and between the inner horizon and the outer horizon, something like a lasing type of phenomena, which goes by the name of the black hole regime, that happens. So this also happens here. The major difference here, now this is a full 2D structure. So therefore, the structure of such cavity is, rather than going to be a linear cavity, it is something of the form of a ring cavity. We also calculated the density-density correlation, because typically at the event horizon, the created Hawking pair. So this is something which can be detected from the density-density correlation, and we have also find out the Hawking temperature. So the Hawking temperature formula has one piece which is very similar to the scalar case, whereas the other piece which comes from the effect of the spin orbit coupled parameters. So we have separated it out. Of course, we have taken here the gravitational analogy, assuming that that thing is going to give you the right value of this Hawking temperature. One can also try to directly calculate the Bogoliubov-Digenais spectrum, and from there infer the Hawking temperature. So from here we have evaluated these two quantities, and here is the plot of that. So this quantity can also be experimentally measured, this 2-point density-density correlation functions. And here one of the very important difference as compared to the scalar condensate is that, since this particular expansion is anisotropic, at a higher value of anisotropy, this particular correlation pattern also started showing the strong feature of the anisotropy, which you can compare by considering the left one and the right one. So the left one is for a lower value of this anisotropy, and the right one is for a higher value of this anisotropy. So this is the corresponding result. So I will now come to the conclusion that spin orbit coupled BEC, this particular system has already been experimentally realized by several groups, and it's not too hard to imprint such a potential on that. It's a potential candidate for realization of rotating sonic black hole. Its metric can be mapped to a btjet rotating black hole matrix in the hydrodynamic limit. And stratified, one of the very important things is that stratified layers are formed in the supersonic cavity due to the presence of modulated density, signature of the formation of a black hole laser. And the anisotropy present in the system distorts somewhat the shape of the horizon, also causes the flow to be irrotational. So this is rotational and anisotropic correlation behavior in the corresponding Hawking radiation pattern. So these are the some additional features which we believe will come into this rotating black hole. So this was already in the ConMat. At this moment it is under the peer review process. So all the details of these calculations are available here. Thank you for your attention.
Yeah, we have time for a few small questions. So are there? Yeah.
Yeah.